Welcome to Probability Theory and Statistics. Today we are going to explore a foundational concept called discrete random variables. If you have ever played a board game, flipped a coin, or counted the number of emails in your inbox, you have already interacted with this idea without even realizing it. By the end of this video, you will understand exactly how mathematicians translate these everyday random events into clean, predictable numbers. Let us dive right in. To start our journey, let us think about why this concept matters before we define what it is. Imagine you are playing a board game and you roll two dice. You do not care if the red die shows a 2 and the blue die shows a 3. You only care that the total sum is 5. You just used a random variable. It is simply a translation rule that takes a messy real-world event and turns it into a useful number. We use the word discrete when these numbers are separate and countable, like whole numbers. You can have 5 customers in a store, but never 5.5. Now that we understand the intuition, let us look at the formal mathematical definition. A discrete random variable is defined as a function that assigns a specific, countable real number to every possible outcome in a sample space. Let us break that down. The sample space is just the complete list of everything that could possibly happen, like getting heads or tails. The function acts like a machine, stamping a number on each outcome. Countable means you can list the numbers out, like 0, 1, 2, and 3. We usually represent the general random variable with a capital X, and the specific number it takes with a lowercase x. With our variable defined, this brings us to an important question. How do we describe the likelihood of each specific number occurring? We do this using a probability mass function. Conceptually, this is just a mathematical formula or table that tells you the exact probability of the random variable landing on a specific value. In this equation, the capital X represents the random variable itself, like the number of heads in a coin toss. The lowercase x represents a specific number it could equal, such as 0 or 1. The capital P stands for probability. So the left side reads as the probability that the random variable x takes on the exact value x. If the probability increases, the event becomes more likely to happen. Now that we have our notation, we must establish the boundaries of these probabilities. This formula represents the first strict rule. The probability of any specific outcome must be a number between 0 and 1, inclusive. Conceptually, this sets the limits of reality. A probability of exactly 0 means the event is completely impossible. A probability of exactly 1 means the event is absolutely certain and will happen every single time. In the real world, this means you cannot have a negative chance of something happening, nor can you have a chance greater than 100%. If you ever calculate a probability and get a negative number or a number bigger than 1, you know immediately that a mistake was made. Following that first boundary, we have a second fundamental rule that governs the entire system. This formula uses the Greek letter sigma, which is a mathematical command that means add up everything. Conceptually, this tells us that if we take the probabilities of every single possible value that x can be and we add all those probabilities together, the total sum must equal exactly 1. In plain English, this means that something from our list of possibilities is absolutely guaranteed to happen. If the sum is less than 1, it means we are missing an outcome. If the sum is more than 1, our probabilities are overlapping or miscalculated. Before we move on, let us see this with a concrete example. Suppose we toss 2 fair coins into the air, and we want to study the number of heads that appear. We are given 2 coins, and we need to find the probability of every possible value. We choose to define our discrete random variable x as the total number of heads. First, we must list the sample space, which is every possible way the 2 coins can land. They could be tails tails, tails heads, heads tails, or heads heads. Since there are 4 equally likely outcomes, each specific combination has a 1 in 4 chance of happening. By counting the heads in each outcome, we see the possible values for x are 0, 1, and 2. Continuing with our coin toss, we will now apply our probability mass function to these specific values. We start by calculating the probability that x equals 0, which means we get exactly 0 heads. Looking at our list, the only way to get 0 heads is if both coins land on tails. Since this is just one specific outcome out of the 4 possible outcomes, the probability is 1 divided by 4. Next, we calculate the probability that x equals 1. This can happen in 2 different ways. Either the first coin is tails and the second is heads, or the first is heads and the second is tails. Because there are 2 successful outcomes out of 4, the probability is 2 divided by 4, which simplifies to exactly 1/2. Now we will find the final probability and verify our work. We calculate the probability that x equals 2, meaning both coins land on heads. Just like the 0 head scenario, there is only one specific way this can happen. Therefore, the probability is 1 successful outcome divided by 4 total possible outcomes. Finally, we must check our work using the second rule of probabilities we learned earlier. If we add 1/4, 1/2, and 1/4 together, it equals exactly 1. This proves our calculations are correct and complete. Physically, this final answer tells us that if we flip 2 coins many times, we should expect to see exactly 1 head about half of the time, which perfectly matches our real-world intuition. To truly grasp what we just calculated, let us look at this visually. Here we see a graph representing the probability mass function for our coin toss. Walk your eyes along the horizontal axis, which shows the number of heads, 0, 1, and 2. Now look at the vertical axis, which shows the probability of each event. The blue bars rise to match the probabilities we just found, 0.25, 0.50, and 0.25. The most important thing this diagram teaches us is the empty space between the bars. Notice how the bars only exist at the exact whole numbers. This visual gap perfectly illustrates the word discrete. The variable jumps directly from one value to the next without ever taking on fractional values in between. Now that we have mastered a simple coin toss, let us tackle a slightly more applied, real-world example. A factory produces computer mice, and historically, 10% are defective. An inspector randomly selects 3 mice to test. We are asked to find the probability that exactly 1 mouse is defective. We define our discrete random variable, y, as the number of defective mice. To solve this, we first find the probability of one specific sequence, finding a defective mouse first, followed by 2 good mice. Because the selections are independent, we simply multiply their individual probabilities together. We multiply 0.1 for the defective mouse, by 0.9 for the first good mouse, and by 0.9 again for the second good mouse, giving us 0.081. Building on that single sequence, we must account for the other possible orderings to get the full picture. The single defective mouse could be the first one tested, the second one tested, or the third one tested. This gives us 3 distinct, equally likely sequences. To find the total probability that our random variable y equals 1, we must multiply the probability of a single sequence by the 3 possible ways it can happen. This ensures we capture every possible way the event can occur. Multiplying 3 by 0.081 gives us a final probability of 0.243. Physically, this means that if the inspector repeats this test many times, they will find exactly 1 defective mouse about 24.3% of the time. Having solved these examples, you might wonder how this applies outside the classroom. Understanding discrete random variables is absolutely crucial for making smart decisions in the modern world. Whenever a business needs to manage inventory, they use these variables to predict the exact number of products customers will buy tomorrow. Call centers use them to calculate how many phone calls will arrive in the next hour, ensuring they have enough staff on duty. In computer networking, engineers use them to model the number of data packets that might be lost during transmission over the internet. Without this mathematical tool, businesses and engineers would be forced to guess blindly, leading to wasted money, crashed servers, and terrible customer service. We have covered a lot of ground today, so let us reinforce the most important ideas. First, remember that a discrete random variable is simply a mathematical rule that counts distinct, separate outcomes of a random event, translating messy possibilities into clean, whole numbers. Second, by using a probability mass function, we can map out the exact probability of every possible number occurring. Finally, always remember the two golden rules. Individual probabilities must sit between 0 and 1, and the sum of all probabilities must equal exactly 1. You have now successfully covered the full topic of discrete random variables. Mastering this concept is your first major step toward understanding all of modern statistics, and you are well on your way.